She got her PhD in 2011 from the University of Santa Cruz, University of California, Santa Cruz. After that, she took a Pappalardo Fellowship at MIT for the next 3 years, and now she's currently a Hubble Fellow at the Harvard Smithsonian Center for Astrophysics. But she's not going to be there for long. In the fall, she's moving to Ohio State University, where she's starting a faculty position there in the astronomy department. Her research focuses on topics associated with supernovae, stellar feedback, and the ISM, where she tries to bridge the gap between observations and theory. So yeah, we look forward to hearing more about that.
Thank you. I'm very happy to be here. Thank you for waiting during all of our technical difficulties. So I'm going to talk about stellar feedback. This is a very hot topic right now. A lot of people even think this is just a made-up word that doesn't actually represent anything, but it does, and I'll show you in particular how we can use multi-wavelength observations in order to probe different mechanisms of stellar feedback and what its dynamical role is on the interstellar medium. So if anyone has ever seen my talks before, you know that I like to start with my conclusions. And so my conclusions are that stellar feedback plays an important role on the small scale, but has an impact on the large scale as well of entire galaxies. And despite this fundamental influence, stellar feedback is often cited as one of the biggest uncertainties today in star and galaxy formation models. And I'll talk about why it's considered to be very uncertain. And then I'll talk about how we can use current and future multi-wavelength observations in order to constrain the relative role of different stellar feedback mechanisms in different environments. And when we apply this technique, this approach to lots of different star-forming regions, we can begin to understand what the relationship is between all the different mechanisms. And this is what we find. We find that photoionization heating is what dominates in most evolved star-forming regions. Then the dust and stellar winds contribute about equally, and then finally radiation comes in last place. But this sort of relationship between these different mechanisms depends on the mass of the star cluster that is contributing the feedback. It also depends on the age of the star cluster. So we'll talk about certain cases where this trend does not hold up. And then finally, I'll talk about work that we've started to do to constrain cosmic ray feedback. And I'll show you how we use gamma ray observations to constrain the cosmic ray diffusion length and what controls the propagation of cosmic rays in external galaxies. So just so that we know what I'm talking about when I say stellar feedback, I mean the ejection of energy and momentum by stars. And people often think of supernovae as the only mode of stellar feedback, but there's actually many different modes. So this is a list of those modes. First, you have direct radiation from stars. The radiation can couple to the gas and exert a pressure on that gas. Then we have dust process radiation. So some of that radiation is going to be absorbed and re-emitted by the dust. That can have an associated momentum associated with it. We have photoionization heating, stellar winds and supernovae, protostellar alphas and jets, and then high energy particles, which are accelerated by stellar winds and supernovae, and that's commonly called cosmic rays. So all of these different mechanisms come together. They have very important implications both on small and large scales. So I'm going to go over some of those that I think are the coolest ways that feedback is important. So number one is that feedback is necessary in order to form realistic looking galaxies. This was first appreciated in the late 1970s, that if you have a galaxy formation model which does not include any feedback, then all of your baryonic material is going to accrete to the center of your dark matter potential well, and you're going to have very dense gas right in the center. All of the gas is going to be converted to stars. You're going to end up with a bulge which is way too big. It has about 10 times too much mass in stars. And because all your gas is consumed, then no more further star formation can occur, and you end up with no sort of extended disk structure and just this big clump of gas and stars in the middle. If you do incorporate feedback, then what happens is it acts to remove low angular momentum gas from the center, so you end up with a much more realistic sized bulge, and as well as the extended disk structure. So in order to get a galaxy like our Milky Way, we need stellar feedback. Another way that it's important is that stellar feedback is necessary in order to account for the star formation histories of a galaxy. So this is true both in simulations as well as observations. So in terms of theory, it was shown nicely in a paper by Phil Hopkins where he compared the star formation rate of a Milky Way-like galaxy as a function of time if you have feedback or no feedback. So in the absence of feedback, all of your gas is converted to stars right when your simulation starts, and you end up with a huge star formation rate, like after not very long time, a few hundred meg years. And because all your gas is consumed consumed, then your star formation drops precipitously, and then you end up with a much too low star formation rate at late times because there's no gas available. However, once you do incorporate feedback in the simulations, it acts to sort of reduce the initial star formation that happens, and then it self-regulates. So then you end up with a very sort of almost flat profile as a function of time for the star formation rate. So that's what people are talking about when they say that feedback is a self-regulating process. Observationally, it manifests itself as what we know as the Kennecott-Schmidt relation. So this is the empirical relation between the star formation rate and the gas surface density. And what this relation tells us is that in one dynamical time for a galaxy, only 2% of gas is converted to stars. And this relationship seems to hold for everything from dwarf galaxies all the way up to these big starbursting galaxies. So this tells you that this is a very fundamental phenomenon that occurs in all different kinds of galaxies, and something ties all these things together that causes the star formation to be very inefficient. Another way that stellar feedback is important is that it is necessary in order to launch galactic scale winds. So if you have feedback in a galactic disk, it can give the gas in the disk a velocity which will escape, and then you'll end up with these large scale outflows that we see in nearby galaxies like M82, as well as all the way up to high redshift, where we see that material is ejected tens to hundreds of kiloparsecs away from the galactic disks. On the small scales, I like to demonstrate that stellar feedback is important through a very simple order of magnitude problem. So in the solar neighborhood, we have about 10 to the 9 solar masses worth of gas, of molecular gas. And if that molecular gas was just subject to gravity, it didn't have any external forces, then all of that gas would collapse on a free fall time, which is given by the density of the gas. And for a typical density, the free fall time is about 4 megayears. So now, if we just had gravity and no feedback, then that 10 to the 9 solar masses worth of gas would be converted into stars in 4 megayears, and you'd have a star formation rate of 233 solar masses per year. Now, the actual star formation rate in the Milky Way nearby is about 1 to 2 solar masses per year. So that tells you that locally, there's a 1% efficiency of converting gas to stars per free fall time. So not only is star formation inefficient on galactic scales, it's also inefficient on the very small scales of individual clouds. So I just highlighted some of the ways that I think feedback is important, some of the coolest ways, but there's other ways that maybe you find cool, so I just wanted to give a full list here. So other ways that I haven't highlighted are that it's important for the formation of bulbous dwarf galaxies. Observationally, it's important to reproduce the galaxy luminosity function as well as the mass metallicity relation. On the small scales, there's lots of different effects. Number one is that it's important to produce the multi-phase structure of the interstellar medium. It's important in order to disrupt and destroy giant molecular clouds on tens of megayear timescales, which is what's observed. It possibly drives turbulence and also possibly triggers star formation. So obviously feedback is important and has a profound effect on both small and large scales, but it's often cited as one of the most uncertain things in models today. And I think there are 3 reasons why stellar feedback is cited as uncertain. Number one is the dynamic range. So you have stars, a star cluster is about 1 parsec across. These individual stars, which are AU scale systems, are going to deposit energy and momentum into the ISM. That is going to shape the giant molecular cloud with which the stars form from. That has a scale of about 100 parsecs, and then that shapes entire galaxies, which the disks are 10 kiloparsecs or so across. So this is more than 5 orders of magnitude in dynamic range. This presents a big challenge for theorists because they have to resolve small structure as well as big structure. For observers, it presents a challenge to us because we have to be able to see the individual stars that are powering the regions, and we have to be able to see the large-scale effect. The number two reason why I think stellar feedback is cited as uncertain is because there are many different mechanisms. So when we have simulations, we have to incorporate all of these different things. When we have observations, we need to try to see what the role is of all these different things. And depending on what kind of system you have, what kind of environment, what age, you're going to have different mechanisms dominate at different times. So for example, let's say I have a star cluster which has no massive stars, only stars below 5 solar masses. Then all of the mechanisms go away, basically, are not important, and protosolar outflows and jets are mostly what is depositing momentum into the ISM. Now, if I instead have a high mass star cluster, by which I mean you have lots of O and B stars, then all of the other mechanisms are important and protostellar outflows and jets are not. Now, another way that it can change is based on the age of the star cluster. So this is a nice, in this paper by Oscar Gertz, he showed what a 10 to the 6th solar mass star cluster, what kind of energy it deposits as a function of age for that star cluster. And what I like about this is that it shows that right as the stars turn on, you get a big deposit of volumetric luminosity, radiation from the stars. And that's going to have a dynamical impact right when the stars turn on. By contrast, supernovae happen after about 4 megayears for the most massive stars. So when we think about supernova being the only feedback mechanism that's important, that's not quite true because it takes 4 million years for that to happen. So that means that this radiation and the stellar winds have been acting for 4 million years before any supernovae even occur. So it's important to consider the age of the star cluster as well, given that these mechanisms change as a function of time. And then the other way I want to highlight why it's important to consider many mechanisms is that when they've done simulations to see what kind of galaxies you end up with, depending on which feedback mechanism you consider, they end up with widely different kinds of galaxies at redshift 0. So this is a really nice paper called the Aquila comparison project, where they took 13 different galaxy formation simulations and just said, okay, what if we only consider supernovae? What if we do supernovae and radiation? What if we do it this way or that way? And what does the galaxy look like at redshift 0 when we do different mechanisms? And it turns out that they change, the galaxies at redshift 0 change very dramatically. They have major differences in morphology, radius, gas fraction, stellar mass, and star formation history. So for example, the mass in stars at redshift 0 varies by 1 order of magnitude, and the star formation rate at redshift 0 varies by 2 orders of magnitude, depending on which mechanism you consider. So it's very important to have realistic implementation of these mechanisms and to consider all of them and not just one. So the third reason why I think stellar feedback is often cited as uncertain is because the lack of observational constraints. So I already said that we have lots of mechanisms, and depending on what wavelength you're looking at, you can only probe one mechanism. So really we need to span the entire electromagnetic spectrum in order to constrain these different processes. Everything from the radio to get the photoionization effects, optical and infrared to get the radiation, you want millimeter and IR to get the protostellar outflows, and then you want X-rays and gamma rays to get the stellar wind supernovae and cosmic rays. And fortunately, we are really in a golden era in terms of observations because we have awesome telescopes at every single wavelength, and we can use those to compare and contrast the different feedback mechanisms. So I think most of us are familiar with this poster, which is commonly shown for like EPO things, right? It's what the Milky Way galactic plane looks like across the electromagnetic spectrum from the radio all the way to the gamma ray. So we know that we have all these data available so we can compare and contrast them. But because there's so much data available now, we can not only do this sort of analysis for the Milky Way, we can do it for external galaxies as well. So for example, these are images across the electromagnetic spectrum for the large Magellanic Clouds. You have radio, infrared, optical, X-ray, and gamma ray. And these are such good data below subarc minute resolution that we can begin to compare all of them in order to understand what the relative role of the different mechanisms are in star-forming regions. And so a big question that one should have when they're listening is, how in the world do you go from data to actually constraining the feedback? What do you measure, and how do you compare these things? And so I think there are 3 different ways that observers can tell which feedback mechanism dominates. Number 1 is based on the velocity of the gas. This is very simple. You can do spectroscopy, see how fast your gas is moving, and that can tell you something about what dominates. So for example, this is 30 Doradus, the giant H2 region in the LMC, and Yuachu did optical spectroscopy of the region and showed that there were 5 different shells that were moving at velocities of 25 to 300 kilometers per second. Now, the sound speed of 10 to the 4 Kelvin gas, so photoionized gas, is 10 kilometers per second. So what this tells you, the fact that the shells are moving at faster than the sound speed of the 10 to the 4 Kelvin gas, means that something besides the photoionization is driving the dynamics of the region. By besides, I mean that we have stellar winds, supernovae, or radiation. So if your gas is moving faster than this speed, you know that something else must dominate. Number 2 is based on the line ratios. So for those of you who work on galaxies, you're probably familiar with the BPT diagram, which is that if you take these 4 very bright optical emission lines, you can tell whether your emission is dominated by, of your galaxy is dominated by star formation or by AGN. This is just based on your spectral shape. And it turns out that the BPT diagram can be done not only for whole galaxies, but for individual H2 regions. And it turns out that if you do individual regions, if your feedback is dominated by photoionization, you're going to fall in the bottom left. If you are dominated by hard photoionization, which I mean shocks, stellar winds, etc., then you're going to fall in the top right. This is really nice because you don't need to spatially resolve your star-forming region in order to produce this diagram. You can just get what the line ratios are for unresolved regions and be able to tell what dominates the feedback. Number 3, which is my method, is to assess the pressures associated with the different mechanisms. And I'm going to show you how we did this for 32 H2 regions in the large and small Magellanic Clouds. So this is the LMC and SMC for those who aren't familiar. And the regions that we're going to look at span a range of properties. They have radii that span like 2 orders of magnitude, H alpha luminosities that span 4 orders of magnitude, and central star cluster masses that span 1 order of magnitude. And we picked the Magellanic Clouds for a variety of reasons. There's several advantages to looking at things in the Magellanic Clouds versus other sources. Number 1 is the proximity. Both of them are 50 and 61 kiloparsecs away, so we're able to spatially resolve individual stars as well as the overall shape of the galaxy. It's been well studied across all wavelengths at resolutions less than an arc minute, sometimes less than an arc second, and we can exploit those data to look at the feedback. There's low obscuration, which means that we can see the stars that are powering the H2 regions. It has a face-on orientation. This part is very important because we don't have the line of sight confusion like we do in the Milky Way, and we don't have the distance uncertainty like we do in the Milky Way. We can assume that the entire galaxy is 50 kiloparsecs away and probe it a lot better without having any of the uncertainties like we do.
You're saying the LMC is the SMC is face on?
The LMC is face on, the SMC is a little bit more
Well, some people think the SMC is much more deep than it is wide. So that's the result from Cepheids.
Yeah, it definitely, the LMC is much more face on than the SMC. The SMC is a little bit more angled. It's not quite like the galactic plane where it's just literally all edge on. It's still, so there is some depth to it, you're right.
Because the SMC and Cepheids looks like L.
Yeah.
The Cepheids are young stars.
Mm-hmm. Okay, so, and then lastly, the reason why it's good to look at the Magellanic Clouds is because there's active star formation. If we want to see the effects of massive stars, we want young stars that have just formed. And so our test case source was 30 Doradus, which is the giant H2 region here. We're going to zoom in on it. So this is a 3-color image of what 30 Doradus looks like. This is the most, let's see, it has 50,000 solar masses worth of stars at its middle, tons of OB stars, lots of Wolf-Rayet A stars. Depending on who you talk to, some people claim they have stars up to 300 solar masses at the middle, which is sort of crazy, but kind of cool if it's true. And it has these 5 shells. This was the example I showed when I talked about optical spectroscopy. And so this whole thing is powered by this central star cluster right in the middle. And you see the molecular gas with the CO contours that has been disrupted by the massive stars that are acting in the region. And 30 Doradus has been really well studied across the entire electromagnetic spectrum. So we're going to measure the pressures associated with all of the different feedback mechanisms. But on top of that, we're going to measure them as a function of position across the region. So we have such good data that we can divide this whole thing up into 441 little boxes and measure the pressures associated with the feedback mechanisms across these whole regions. So I'm going to take you through how we go from the data to the pressures, and I'm going to break the cardinal rule. One of the cardinal rules of talks, I'm going to show you a table because I think it's important just to organize all your thoughts. I think you can handle it even though it breaks the rules. So the first thing we're going to measure is the pressure associated with radiation from stars. This is the radiation that couples directly to the gas, and it is given by the energy density of the light that's emitted by the stars. And here we're assuming that it couples because 2/3 of the momentum flux of the light is in ionizing photons, so it's very easy to couple. And the way that we get this energy density is from the bolometric luminosity of the stars, and that's given by UBV photometry. So there's all these really beautiful Hubble images and ground-based images that map the entire region that's 150 parsecs in radius. And what we did was we took each of our little boxes and we said, what is the pressure felt at the center of this box from all roughly 10,000 stars that have been observed in the region? And then we add them together and we produce our map. So we took these data and we produced this map for the direct radiation pressure across the source. You can see that it is dominant in the center, it's the highest in the center, right where the central star cluster is, and it falls off with a radius going away from the central star cluster. And it's not quite a perfect 1/r² dependence because there are other star clusters in the region. So up here, there's a little star cluster that's contributing some to the radiation pressure in the region. But overall, it's very sort of 1/r² in terms of its shape. The second component we're going to consider is the dust process radiation pressure. So this is the component when you have light that's absorbed by the dust, re-irradiated by the dust, and then maybe trapped in the H2 shell and contributes momentum to the shell. And this is given by the energy density of the light that's absorbed by the dust. You can get a handle of that parameter by doing infrared SED modeling. So this is what infrared SEDs look like. If you have dust that's heated a lot more, your SED is going to shift to the left. So based on where your SED peaks, you can tell basically how much radiation has been absorbed by the dust. So we use Spitzer data for the SMC and the LMC, for 30 Doradus, and we find this, that the dust process component is not as dominant as the direct component, but it still is fairly significant. This is the same color map just so we can compare and contrast. And we see that the dust process component seems to dominate out at the edges where the shell is currently. The third component we consider is the warm gas. This is the gas that's photoionized and heated to 10 to the 4 Kelvin temperatures. It's a gas, so we have a gas pressure. It's given by the density and temperature of the gas. The temperature is set by the balance of heating and cooling, and it's 10 to the 4 Kelvin. So really we just need to measure the electron density. There's a lot of nifty ways that one can measure the electron density of gas. This is straight out of Rybak and Lightman. And the way that we do it is using the radio emission at 3.5 centimeters, which is dominated by free. You just basically stick in the flux and you get the electron density. And another way that one could do it is in the infrared, take ratios of fine structure lines and get the density. And so this was done by Remy and Debito for the very center of 30 Doradus. And so this is the map that he produced using the infrared, and on the left is the map that I produced using the radio data. And you can see that we have very similar data. So we derive the same answer even though we use 2 totally different wavelengths. And so we put that together to produce the 10 to the 4 Kelvin gas pressure across the region. You can see that it's not, still we have the direct radiation is dominating in the center. The warm gas seems to be comparable to the dust, and it does seem to be dominant at the shell, basically what's pushing the expansion right now. The last thing we'll consider is the hot shocked gas. So this is gas that is shock heated by the winds and the supernovae to 10 to the 7 Kelvin temperatures. This shocked gas emits in the X-ray, so we use X-ray data to measure this pressure. In particular, we measure the density and the temperature from X-ray spectral modeling. So the X-ray data are dominated by Bremsstrahlung emission. This is what an X-ray spectrum looks like for those who are not familiar. And so you have this nice curve. Depending on the sort of amplitude of the curve, you can get a handle of the density. And depending on where this curve turns over, you can get a handle of the temperature. So we extracted spectra and modeled them across our little boxes to get the density and temperature across the region. This is what we get, temperature and density. You can see that the temperatures are vary quite a bit across the region. It turns out that if I were to overplot what the H2 region looks like, all of the places where you have elevated temperatures are where the hot gas is impacting the shell of the H2 region. The electron density for the hot gas seems to be pretty uniform across the region. The only exception is right down here where there's actually a supernova remnant that's heating the gas. So we put that together to get the hot gas pressure across the region, and this is what you get. You can automatically see with your eye that it's not as significant as the other components. It doesn't seem to contribute very much at all. All of these little blue shapes correspond to the areas of the occupying the shells, the 5 shells of the region. But in general, it seems to not be as significant as the other components. Now, because I did this sort of systematically, I can sort of bin these points together as a function of distance to calculate what are the pressure terms as a function of distance from the central star cluster. And so this is what I got for the relationship. So we have the direct radiation pressure in dark blue. This seems to dominate up to a radius of about 75 parsecs. The dust and the warm gas pressure seem to be comparable out to about 50 parsecs, at which point the warm gas takes over. So keep in mind that the shell of the H2 region is about here right now, which means that the photoionized gas is what's pushing the shell currently. By comparison, the hot gas is not significant at all. It's a few factors below the other components. And so I want to talk about 2 different implications for this plot. Number 1 is that radiation pressure dominated at early times for this H2 region. When the radius of the H2 region was smaller than this, the direct radiation was driving the motion of the shell. And a radiation-dominated H2 region evolves slightly differently than our sort of classical H2 region. In particular, it has more momentum imparted to the shell, accelerated expansion at early times, and the most important point is that because you have more momentum imparted to the shell and accelerated expansion, you have a shell that expands faster than the escape velocity of the central star cluster and faster than the sound speed of the 10 to the 4 Kelvin gas. Now, the reason why this is important is because the radiation gives the gas enough velocity for it to escape the central star cluster and for it to halt star formation in the region. Whereas the sound speed of the 10 to the 4 Kelvin gas would not give the gas enough velocity to escape the cluster. So essentially it means that radiation is sufficient at halting star formation, whereas the photoionization wouldn't be. The other implication I want to discuss is why is the hot gas pressure so low? And we think that the answer is that the hot gas is not confined in the region. And so I made a cartoon picture to explain this. So on the left side, if you just have stellar winds and supernovae that are going off, but they're going off into, there's no confinement, there's no shell, it's just floating, being lost from the region, then you end up with a very low pressure and low X-ray luminosity because all of that energy is lost. In the converse scenario, if you have a completely filled shell, no holes in the shell, then all of your wind and supernova energy is going to be trapped in the bubble. You're just going to keep building up that energy, and you're going to end up with a very high pressure and high luminosity. And the intermediate case, which is obviously much more physical, if you have a shell that's expanding into an inhomogeneous ISM, there's going to be holes that are punctured into the shell, and those holes are going to be a place for the hot gas, for that wind energy to be lost. And so you end up with partial confinement, and this gives you an intermediate pressure and an intermediate X-ray luminosity. So the picture that we're developing is that probably 30 Doradus represents a region that has partial confinement. That is, that the hot gas is not fully confined. Some of it is trapped. That's where you get the elevated pressures. But otherwise, it seems to be leaking from the shell, and that's why it is not dynamically significant. Now, I said that 30 Doradus was our test case source. So we did this analysis for 32 H2 regions circled here. They span all those different properties that I mentioned, and we want to measure the pressures for all of them. Now, because we don't have as wonderfully beautiful data for these sort of lesser known H2 regions than 30 Doradus, which is one of the big ones, what we did was, instead of mapping the pressures across the sources, we just measured the total pressure that's felt at the shell. And so we use similar data. You guys remember my table. It's basically the exact same procedure, and we're measuring the 4 components across these 32 H2 regions. And so these are the results. So it's kind of a confusing diagram, but I'm going to explain it. But if you zone out, this is what the answer is. So what I did was I plotted the individual pressure components as a function of the total pressure in a region. And what this does is it tells you how much an individual component contributes to the total pressure. So depending on where a data point is relative to this line, it tells you how much something contributed. So if we look, we see that the orange points, which are the photoionized gas heating points, the 10 to the 4 Kelvin gas pressure, those contribute about 80% to the total pressures of the region. So that's what's dominating the dynamics of these regions. Then you have the dust and the X-ray, which are contributing about 10% to the total pressure. So factors of several below what you get for the warm gas. And then in last place, we have the direct radiation, which is only contributing about 1% to these regions. So you can see that, that's the trend that we get, that the photoionization dominates, then the dust and the winds and supernovae contribute, and then the radiation not so much. And the beauty of doing this for lots of sources is we can begin to compare and contrast them and try to see what the trends are. And so with that hope, I plotted what the individual pressures are as a function of radius of the H2 region, hoping that maybe there would be an astonishing trend that you would see the pressures are elevated for smaller H2 regions because they don't have holes in their shells yet. But alas, it does not appear so. You can squint and try to convince yourself that the smaller H2 regions have higher pressures, but in general it doesn't appear that way. And I think the reason is because the sample that we're looking at are all evolved H2 regions. These are sources that are between 4 and 10 megayears old. We want to consider much different times in order to see what this actual evolution is. And so with that in mind, we thought about how do the feedback trends change as a function of time or age of the H2 regions. And in particular, we decided to look at ultra-compact H2 regions. So for those of you who are not familiar, these are regions that are the very earliest point, or they're the regions that are produced right as the massive stars turn on. They have radii of less than 1/10 of a parsec, and they have densities of greater than 10 to the 4 particles per cc. Although it sounds really extreme and crazy, they have discovered about 200 of them now in the Milky Way, and we have multi-wavelength observations that we can use to do our analysis. And so when we add those ultra-compact H2 regions to our plot, then we begin to see the trend. So these are the ultra-compacts up in the top left. These are my evolved H2 regions in the bottom right. So you can see definitely now, okay, there's a trend. The younger regions have much higher pressures, and the pressures decrease with time. In some cases, depending on the mass of the central star cluster, you can get the radiation pressure to dominate at these early times. So these are the blue points up here. In order to get radiation dominating H2 regions, you really need young, massive clusters to be powered that way. But this is sort of our first step in understanding how feedback changes as a function of time. So I've told you a little bit about what our results are for these top 4 different mechanisms, and we have not yet considered protostellar outflows and jets. One of the reasons is because you cannot spatially resolve protostellar outflows and jets in the Magellanic Clouds. You need to look at sources that are in the Milky Way, so we haven't done that yet, but we can potentially look at some of the closest molecular clouds in order to understand how protostellar outflows contribute momentum. But we have started to consider how cosmic rays are important. And so I want to take you through some of the things that we've been doing lately. This is very new stuff, so I'm still sort of parsing it and figuring it out. But I thought it was exciting, so I wanted to show it to you. So, what are cosmic rays? For those of you who are not familiar, cosmic rays are generally particles that have energies above 1 GeV. I know this is like a super 80s-tastic plot, but I thought it demonstrated very nicely what I wanted, which was to show you what the energy spectrum looks like as a function of energy for cosmic rays. So everyone likens the cosmic ray energy spectrum to a leg, and because there are 2 breaks, which they call the knee and the ankle. And so above the knee, the thigh of the spectrum is from supernova remnants based on energetics arguments. So within our own Milky Way, between the knee and the ankle, the shin is from probably another galactic source, maybe pulsar or something else. It's not actually clear. That's an unsolved mystery. And then below the ankle, the foot, is from extragalactic sources like blazars, AGN. And generally cosmic rays, so this is the spectrum as we observe it on Earth, and generally when people talk about cosmic rays, they're talking about both electrons and protons. And roughly 99% of cosmic rays are protons and ions, and only 1% is electrons. That's important, depending on what you're looking at. But in general, cosmic rays are important for a variety of reasons. I wanted to highlight a couple of them just because I know people are less familiar with cosmic rays in general. And so cosmic rays are one of the only things that can penetrate dense gas that has a density above 10 to the 3 particles per cc. As a consequence, they are what ionizes molecular gas, and they are the primary heating mechanism of molecular gas. They're very important in the regimes of star formation. Number 2 is that they bombard oxygen and nitrogen to produce all of the lithium, beryllium, and boron in the periodic table. So they are responsible for producing some of the lightest elements. Number 3 is that cosmic rays are very important to the total ISM energy budget of the Milky Way. It contributes about 10 to 20%, and it's comparable in energy density to the magnetic field and the turbulent energy. So these seem to be connected. And the 4th thing, and the reason why I became interested in cosmic rays, was because they seem to possibly play an important role in the launching of galactic winds. And so the paper that got me excited about cosmic rays is this by Booth in 2013. And it's a simulation paper where they looked at an SMC-like galaxy and a Milky Way-like galaxy, and they said, okay, what does the wind look like if it is dominated by cosmic rays or if it is dominated by thermal feedback? And it turned out that the cosmic ray-driven wind is much more similar to what we observe in galaxies that have outflows like this. In particular, cosmic rays are more gentle launchers of winds, and you end up with velocities and mass loading profiles and distances which are much more comparable to what we see in external galaxies.
So you mean cosmic rays are galactic from which
Within the galaxy, yeah.
So it's that not the thigh thing in between.
Oh yeah. I'm talking about the GeV sort of energy particles, yeah. And that's what dominates in terms of like UF-nu or that sort of thing. So yes, so these are cosmic rays which originate in the disk of the galaxy and are advected out. So I began thinking about how we could probe cosmic rays and cosmic ray feedback, and
Actually, what did they assume the source is to be of the cosmic rays?
the source, they don't.
They can say there's some magic source of cosmic
Yes.
rays that comes.
Yeah, and they make it, they make it 10% of the supernova kinetic energy, which is the
10% of the kinetic energy for supernova.
Yes,
And they assume, okay. Okay.
but it's very ad hoc.
Okay. So there's no like, that's fine.
There's no assumption. They just put in the diffusion basically into their equations, and then it's a pressure signal for the disk. That's all they do.
So there's no estimate of could there be a realistic population of pulsars in this system? And they're probably
No, that's not their thing. No. Yes, that's one way to improve upon. Yeah. Okay. So I began thinking about how we could use observations to probe cosmic ray feedback, and there's a few different ways. Number 1 is using gamma ray observations, and so there are 3 different mechanisms that produce gamma rays that are associated with cosmic rays. 1 is from protons and 2 are from electrons. So from the protons you have pion decay. So pion decay occurs when you have cosmic ray protons that collide with dense ISM, and this collision produces neutral pions which decay into gamma ray photons. In terms of the other 2 processes, those are both from cosmic ray electrons. You have bremsstrahlung emission as well as inverse Compton. And when you get a gamma ray spectrum, this is what it looks like. So these are spectra from the Fermi satellite. And you can begin to sort of decompose it and understand, break down these different 3 mechanisms and how they contribute. You can get this curve in the gamma ray. And so this is sort of a new way, since Fermi was launched in 2008, to really probe the cosmic ray population.
Oh, there's an LMC.
What?
Those are in the LMC.
No, these are actually just galactic supernova remnants. I just did them as basic examples of what a spectrum looks like. So before sort of Fermi and awesome space-based gamma ray astronomy, the primary way that people probed cosmic rays is through cosmic ray electrons, which emit synchrotron radiation. So remember that electrons make up only 1% of cosmic rays. So when they are looking at the synchrotron radiation from cosmic ray electrons, they're only looking at 1% of the population. But nonetheless, it was very important, and the only way we can probe cosmic rays for a long time. They manifest themselves in the X-ray. We can see them along the shock fronts of supernova remnants. And in terms of whole galaxies, the people were very excited about the far-IR radio correlation, which is the primary example of what people say when they say cosmic rays are tied to massive stars. So what this correlation is when you take whole galaxies, it turns out that the far-IR luminosity is correlated with the radio luminosity, and across many orders of magnitude. And so people interpret that as, okay, the far-IR is from massive stars, and the radio is from cosmic ray electrons. So that means massive stars must produce the electrons, the accelerated electrons. And that's consistent with supernovae accelerating the particles. Now, as I mentioned, this day and age we have Fermi, which is a gamma ray telescope. I just put up these basic points just so in case you guys aren't familiar. It was launched in 2008. It has 2 instruments on it. The primary one that I use is the Large Area Telescope, which is taking an all-sky survey at all times. I think it images the whole sky in about 4 hours each day, and it observes from 20 MeV to 300 GeV. And so Fermi, because it's taking the whole sky, it's taken the whole sky, so it has the Magellanic Clouds. So I went and I looked at the initial papers of Fermi studies that were published in 2010. This was using 1 year worth of Fermi data. On the left is the LMC, and the black shows you the H1 contours. And this region right here is where 30 Doradus is, the giant H2 region that I talked about before. So it's very intriguing that most of the gamma rays, which are associated with cosmic rays, originate from the most massive star-forming region there. That's awesome. The SMC is a little bit more underwhelming, so you just have a big blob right in the middle, and there's no real obvious substructure to the emission. Now, when I looked at this, I realized, okay, this is 1 year worth of data. Now we have 6.5 to 7 years worth of data. What do we get now? And then when we can begin to do sort of spatial analysis of the gamma rays and how they correlate with the massive star-forming regions, and how the cosmic rays propagate away from those regions, and how they contribute to the feedback. So we went back and we reproduced the Fermi images of the LMC and the SMC, and then we see a lot more substructure. And we find that the 30 Doradus actually contributes half of the gamma ray flux of the entire LMC. So that's really remarkable. And so you can see the substructure here. There's 30 Doradus again, but we have some gamma rays in the center of the galaxy. For the SMC, we just have a very extended bar. We see the gamma rays are coincident with the bar of the galaxy. So I want to show you a movie of what the gamma ray emission looks like as a function of energy. So we produced images in 8 different energy bins. And what I'm going to show you is, this is the LMC, the H1, just to guide your eye. And let's look at 30 Doradus, which is right here, as a function of energy. So I'm going to play it once and just look at the middle. So we're stepping up from 200 MeV all the way to 50 GeV. So I'll play it one more time. So you can see that there is extended emission up until basically the end, that you have up to 50 GeV photons, most of which seem to originate from 30 Doradus. So that's really exciting. But one thing I want to highlight, though, is that although we have 30 Doradus, obviously right here, we don't have some of the other H2 regions. So in particular, the second most massive H2 region in the LMC is called N11, and it is up here. So let's watch the movie again and watch this area. Just a little bit, but not really.
What's the annual scale of that?
The angular, this is 10 degrees, roughly.
Oh, that's huge. Okay.
Yeah. Each pixel is about 100 parsecs.
Okay. And that corresponds to angular size of?
Angular size of I would say tens of arc minutes. Yeah, or
That's, okay.
10 arc minutes, I would guess, yeah.
Much smaller than the resolution of Earth.
Yeah, your spatial resolution depends on energy, and it's good at high energy and it's bad at low energy. Yeah. So people before in the original frame paper said, oh look, the gamma rays are all coincident with 30 Doradus, and so massive star regions accelerate particles, and that's our picture. But that's not quite it, because yes, there is stuff here, but why is there no emission at the second most massive star cluster? And so there's something else that's going on in this picture. And we can begin to understand by, I'm not going to play the movie again, by sort of looking and comparing the gamma ray significance contours to other wavelengths. So this is the gamma rays in white and the H1 in orange. You can see this is the second most massive region, no emission there. But in general, there seems to not be a very remarkable correlation between these things. We looked at the molecular gas, the H2. In principle, you could have enhanced gamma rays where there is dense gas because the pion decay occurs when cosmic rays collide with dense gas. But it doesn't really seem to correlate very nicely. Then we look at the H alpha, and this is a lot better at predicting the gamma rays. So we see that actually the contours are outlining the massive star regions up here as well. But again, N11 is missing. And so we're beginning to think about why, and we think the answer is the magnetic field orientation. And so we've begun to look at the data taken in the radio, showing you what the direction of the B field is, and comparing it with the gamma ray luminosity. And it turns out that it seems like the emission actually follows the orientation of the field. And so it's some combination of the massive stars do launch, or rather accelerate the cosmic rays, but then the cosmic rays get out because of the magnetic field. And so we're in the process of putting this together and doing a really statistical analysis to show you how cosmic rays propagate, along the field lines versus perpendicular to the field lines. And I think, I suspect that our conclusion will be that it's dependent on the B field. So just to show you the same movie for the SMC, we're going to go through again. You can watch the main point. The second or third energy bin has a really anomalous structure, and so there it is. I don't know what that is, but in general, the emission traces the bar of the galaxy. We'll do it again.
Especially when you get above like 1 GeV, you're only talking like a handful of photons, right? So
Yeah.
So I mean, whether or not the statistical significance of these things are.
Oh yeah. Oh well, I'll get to that in a second, but yeah. So in general, it does seem to just follow the bar where you have a lot of the massive stars. We can do sort of the similar correlations. This is the gamma ray emission and the H alpha. You can see that it's fairly well traced. It doesn't fully trace, but it's pretty good. In the case of the SMC, this is what the magnetic field orientation is doing. It's very ordered. It's just all along this direction, which is actually pointing toward the LMC, which is over here. So in terms of tests of like how the gamma rays depend on the B field, I don't think we're going to get very much for the SMC because it's so ordered. The LMC is much more tumultuous, but in particular it seems to have like a rotating field. And so I think we're going to have a lot better tests there. So we can use these data to get what the gamma ray spectra are, and so this tells you what the significance is of the different energy bins. The error bars are really tiny. And so this is what the spectrum looks like for the LMC total. This is the 30 Doradus, which is half of the flux in basically all of the energy bins. 30 Doradus by itself, and then the SMC. And the reason I wanted to show you this plot is because of how weird the SMC is. So the SMC has a signal all the way up to about 10 GeV, and then it falls off, and then it's not there. And actually, the non-detection of those points is very significant, above 10 GeV. And so I think what's happening is that the particles are getting accelerated in the SMC, and then they escape before they get above 10 GeV. The galaxy is too small to contain the very high energy particles. So I think it's because they have a sort of smaller area to accelerate to propagate, then you end up with a cutoff in the in the spectra. And we haven't seen that in any other galaxies. This is the first time that we've seen it. So I've really just hit the tip of the iceberg in terms of what we can do. Just to like get you a little bit more excited about things we can do in the future. One thing is to compare how the feedback affects the molecular gas. So we're beginning to get all my data on different clouds around star-forming regions. My pointer stops, so I'm just gonna like point now. But this is 30 Doradus right here. This is the central star cluster, and we can begin to understand how the massive cloud, the molecular clouds properties change as a function of, say, distance from the central star cluster and how they're disrupted. Number 2 is looking at feedback in different environments. We can begin to understand if we look at other H2 regions and, say, starbursting environments, low metallicity environments, or emerging galaxies, we can begin to understand the effect that this different environment can have. And then another area that I'm particularly excited about is understanding how galactic winds are launched. So we can begin to use the multi-wavelength data in order to understand what actually launches the winds. And I put up this example from a paper by Alberto Bellato, which is using ALMA data and other wavelength data. And what's really cool about it is it's looking at NGC 253. And so it's an edge-on galaxy. And you have the outflows, which are in blue and purple, I guess. And if you trace the outflows back, you get to here. And it turns out that there are 4 expanding H2 region shells right where all of this material is being launched. And so that's a pretty, significant discovery in the sense that the fact that we can trace the material back to these shells where there are massive stars, we're beginning to understand the connection just by using this multi-wavelength data. And then finally, I think one of the really outstanding questions is how feedback should be incorporated in galaxy formation simulations. You end up with this sort of disaster where it's like, okay, depending on what feedback you consider, you end up with drastically different galaxies. We need to think a little bit more about how to do it. And so they are thinking about it. But I think that's another area where there's going to be a lot of discovery in the next few years. But these are my conclusions, and I can take your questions. Thank you. Any questions?
3 out of the 4 youngest supernova remnants in the LMC are type 1a supernovae, not massive stars.
Yes.
You haven't included type 1a supernovae in this discussion. Why have they been excluded so far? Is there something hard to study about them in terms of their energy input into?
So you are absolutely correct. The youngest supernova remnants in LMC are type 1As. This is very anomalous in the sense that generally people don't think of type 1As as in the disks of galaxies, where you usually expect them to be in the halos because they're older populations. And they are in the Milky Way. They're very high up. They're high latitude. In the LMC, they're not. In the LMC, they are in the rest of the galaxy. And so I absolutely agree that including type 1As is important, and we can do it. We can do it with the data that we have for the LMC and the SMC. I'm just trying to explain why people haven't thought about it yet. And it's mostly the simulators who just haven't included. They always do type 2 core collapse supernova because they say, oh, type 1As take too long and they're far away from the disk.
Also, the energy injections.
The energy injection is the same. Well, it's in kinetic, yeah. It's not in dense gas,
They're not that
though.
far away from the disk. I mean, type 1a supernovae are associated with star formation. If you look at the star formation rates in galaxies, type 1a supernovae happen more often in starburst galaxies. And so
But
it doesn't
they're
happen
delayed,
in,
though.
What?
They're delayed.
They're delayed,
The time scale
but
is
they're
a
in
lot
the disk.
later.
But they're in the disk. They're associated with star formation. So
I guess I disagree with that. It's not necessarily in the disk. They can be outside of the disk.
oh, of course they can, because there may be more than one channel type 1a supernova.
Yeah.
But the dominant supernova, the most common type 1a supernova, is not associated with the local population. It's associated with populations less than 1 billion years old. And that's been shown by all the studies that have been done in blind searches. So there are two types of type 1a supernova, but one of the channels looks like it's a young channel.
Yeah, so the prompt channel is what's going to be really important. And I agree with you that it needs to be considered. I mean, type 1As are 1/3 of all supernovae, and so they are going to contribute.
But they're more energetic, significantly more energetic. But if they're happening outside the disk, then they positive energy. So
Yeah.
they're-
Yeah, I was just explaining why other people don't. I agree with you. I work on supernova stuff, so any other questions?
How about like resolving structures in M31, especially with gamma rays?
Yeah, so I just showed you the Magellanic Clouds for consistency, but I have done M31 also, and you can see one half of M31 is lit up in gamma rays and the other half isn't. It's harder because it's edge on, and so I don't know what it's associated with, but part of it, and they haven't published it. It is, according to all the current papers, it's not detected, but if you go and download the data,
Wait, M31.
M31.
No, M31 is detected gamma rays, confirmed.
Okay,
Yeah, that was, 2010.
okay.
Yeah, and it follows infrared, I think, which is relatively well.
Yeah, but it's only part of the disk. It's not, and I.
That could be true, yeah.
Yeah. Good.
30 Doradus is an unusual object. There, if you look at the other dwarf galaxies like the Sculptor, you don't see something like 30 Doradus.
Yeah.
But 30 Doradus perhaps is very common early on in the universe. So there must be also, in the way you're approaching this, it must be true that it's the smaller H2 regions and clusters that are really dominating the local star formation rate in the nearby universe. Isn't that? I don't work in the field, but
Yes, that's why people always liken 30 Doradus to the early universe, and then when people study the closer stuff, and they say, okay, this is actually what is important. But it is true that your most massive stars in a galaxy are going to dominate the energetics. The most massive star clusters are going to dominate. So that's sort of the motivation. And also just to understand you want to understand all environments, including the extreme ones.
Any last? No.
Okay.